Hello, everybody. So, welcome again after the break. We will continue our session with a presentation from Peng Fei, and he will tell us all about his implementation of an AI system for inference, all based on open source components using OpenCAPI and NVDLA. So, please.
So hello everybody. So I'm really glad to present one of our work here to show that how an open source project can be integrated with another. Because early this morning, Mandy announced that we have more openness in our open hardware ecosystem. We opened our IP, we opened our reference design, we opened our instruction set architecture, we opened almost from the top level applications to low level hardwares for IBM. So I think to demonstrate that IBM's technology can collaborate with the existing open source project is really important to show that we have a really good ecosystem for the open hardware community. So let's talk some of the backgrounds. So my topic is that we are trying to integrate one of the AI inference engine in the community. We are trying to integrate that with OpenCAPI. So for AI, so it's a very hot topic for recent years. We've seen that for previous speakers, I saw that people are trying to accelerate AI, deep learning and machine learning algorithms in database. People are trying to accelerate machine learning algorithms in with different precision of data. And we also see that there are so many companies, including big companies and startups. They are all working on accelerating artificial intelligence workloads all over the world. So to have this accelerator with Power 9 with OpenCAPI, I think is very meaningful. It's very meaningful to the whole open power ecosystem. And then for Power 9, I think Power 9 has an emphasis on the heterogeneous computing, which means Power 9 we have interfaces such as NVLink, CAPI, OpenCAPI, and PCIe Gen 4 to encourage people to connect an accelerator with our CPU, so that the whole heterogeneous computing system can be more efficient with the help of accelerators. So that's why that's also another reason that we want to integrate an AI inference engine with OpenCAPI. And then finally, and why we choose NVDLA. So the full name of NVDLA is NVIDIA Deep Learning Accelerator. So that is the open source project NVIDIA opened to the community in last September. They open sourced the accelerator that has exactly the same RTL code they used for their product. That is in Xavier SoC Tegra system. It is exactly the same RTL code without any modification, without any compromise. So the same RTL code to the community. So it's a very high quality, industrial level, production level open source project. So if we can integrate that together with OpenCAPI, then that would be very meaningful for the real business, for the real partners, because we have so many fantasy, exciting, amazing research works, but seems like for today's FPGA session, I didn't see any of the projects that are based on real product. So that's why we try to do this, try to solve this, fill this gap between the research and the real production. And then speaking about the ecosystem, so let's take a closer look at what is the current status and what we have now. So for the NVDLA, they open sourced this project for last September, and as I have said, they are exactly the same code used in their project, and more importantly, NVDLA they have a really active community in the right now, because I think it's in early this year. Sci-Fi is a company who are focusing on RISC-V CPUs. Sci-Fi, they announced that they have a collaboration with Nvidia to bring their RISC-V core together with Nvidia's NVDLA. So that's a big, it's a I think it's a signal to the community that this kind of open source project can be integrated with a real CPU system. And then, so far as I know, at least in China, there are many small startups. They are based their work on top of NVDLA. So, which means NVDLA is a very, very promising project that worth a try to connect with OpenCAPI. And then on the other side, that is OpenPOWER and OpenCAPI. So, as I have said, Mandy and the whole community, we opened our design. We have our reference design in the GitHub. So you can download our OMI designs. You can download our OpenCAPI board package support codes, and you can also have our lately opened development framework, that is OC-Accel. So all of those things put together means that we have every pieces that has been opened in the community. So the final last mile is that we need to put all of those together: the application, which is NVDLA, and the interface OpenCAPI, and the framework OC-Accel, and the open power system. So we need to put them together to show that the open source community can really deliver business results. And so this is from the open source community's perspective. And if we take a from different angle, we take a look, and from the production perspective, we can see that here is a picture showing for the AI accelerators what kind of solutions we now have for the computer systems. I have two parts, x86 and OpenPOWER. So for x86, we have choose to use Intel's CPU, Nvidia's GPU, and the PCIe interface FPGA, and Google's TPU to accelerate the AI workloads. But for OpenPOWER, we also have similar offerings. But none of these offerings can utilize OpenCAPI right now, because OpenCAPI is really a new technology which has been invented maybe less than 3 or 4 years. So we need a solution to connect a workload together with this interface to show to the customers that this interface can really deliver a real production, and you have a choice to use OpenCAPI to accelerate your AI workloads. So that's the reason, and that's another meaning of this project. So from here, that is the OpenCAPI based FPGA solution for AI workloads. Okay, and then let's take a look at the details of what we have done. So in this picture, we can see that on the right side, this is the FPGA, and on the left side is the host power line system. And on the FPGA, in this green box is the NVDLA hardware. And this hardware, I think, how to say? I'm sorry. So this for this NVIDIA hardware, it was comprised with different engines. So this is the structure of NVDLA hardware architecture. They have different engines: convolution, activation, pooling, LRN, reshape, bridge, DMA, and they have different engines comes together. And we put all of those things onto FPGA, and we interface this IP with OC-Accel, which is the development framework Lu Yong just announced. And we connect this IP with this framework via Accelerator and Axi. Accelerator is used for configuration, register configuration, and Axi, this is the memory mapped interface for data transfer. And then we also have the interrupt, because for this kind of IP, we need the interrupt to have a full functional inference workload. And then, just as I have said that, I'm sorry, this, okay. And then for the host system, for the PowerNet system, we are running our project on a real PowerNet system, which is called project name is 5290 from Inspire. Exactly is IPS, which is exactly the same PowerNet system as IBM's Wistron's Minhawk, and we are using this machine to test our how to say our work. And then all of our work are based on OC-Accel. So I just heard from people that people are waiting for more than 1 year for this kind of framework so that they can use OpenCAPI. But because I'm in China, so I have the VIP access to this framework. So that's why But today, I just after less than 1 hour, we announced the open source of this framework. I already have this project already working with OC-Accel. So this is I think OC-Accel really helps here, because for this kind of open source project, they are Axi interfaced, so they have AXI interface, and you don't want to change that to another interface, for example TRX, because it's really a complicated design. So if you want to change that to TRX, it actually means you need to reinvent this data bridge by yourself. So if we have OC-Accel, then for most of the existing IPs in the community, you can easily just just connect this interface with OC-Accel, then everything is good. So you can easily use OpenCAPI interface by this bridge. And then from the software side, we have two parts. So the first one is that if you want to make your make your software works with hardware, then you need to rely on the drivers. So right now, because OpenCAPI is virtual addressing, so we don't need kernel mode driver. So everything we need is to use the user mode driver from NVDLA. So I will explain more into details on what we have done, what we have modified for their drivers. And then on top of drivers, we have the real inference application, which is going to perform the image recognition, image classification workloads. And then for the FPGA card, I think we can choose the FPGA card from different vendors. Right now, we don't have too much choices, because for OpenCAPI, we have Alpha Data, 89V3, 89H3, and 89H7. And so unfortunately, only 9H7 can fit the NVDLA design, because it's not a small design. So we don't have too many choices, but we're working on that. Hopefully, we will have some vendors from China. They can offer OpenCAPI based FPGA card in the future, maybe next year. Okay. And then for the hardware design, I will explain more on some of the details. That is, right now our whole hardware architecture is based on this multi-engine structure. Inside the FPGA, inside the AFU, we have an AXI interconnect, which can connect to different multiple NVDLA engines. So, and those engines can be managed by a job manager, and the job manager, they have a job queue, and then those multiple engines, they can work together in a multi-process style, but right now this kind of structure is still in development, because we are heavily rely on the support of multi-process from OC-Accel to finish this work. So after OC-Accel can support the multiprocess, then this whole structure can be put together to deliver the high band deliver higher throughput for the AI workloads, because we can put multiple engines into the FPGA, so that you don't need to modify the engine itself. You just duplicate the number of engines, then you can get a higher throughput from the application's point of view. Okay, this is for the hardware, and then let's take a closer look at the software side. I think this is the really how to say charming part of OpenCAPI for the users, because for OpenCAPI we know that it has cache coherency, it has a lower latency, it has high throughput. But according to our own experience working with customers, we found that for most of the existing FPGA projects, to utilize such a huge bandwidth, such a huge throughput, and it's not very common for the existing solutions. So we and don't mention to cache coherency. If you ask the users to say, hey, can you utilize cache coherency of OpenCAPI or any other interfaces? The users, the customers, they will say, what? I don't know how to do that. Because cache coherency is not in their mindset for those FPGA developers. So I think the really charming thing is that attractive thing for OpenCAPI is the virtual addressing for the users, because with virtual addressing, it can really simplify your software stack immediately. So this is the thing that you can feel right now with your for the developers, for the software engineers. So this is the whole software stack of NVDLA. So on the right side, this is the model training part. They have a compiler to transform the trained model to a loadable. This loadable is in flatbuf format, so it's a very standard format invented by Google and used very widely in gaming and a lot of areas. So in this format, then for NVIDIA, they have two kinds of drivers: user mode driver and kernel mode driver. For the user mode drivers, it will take this loadable as input and parse that, and to see how many layers they have and what is the real task they are going to perform. And then for the kernel mode drivers, it's the real part of software code to communicate with the hardware. So user mode driver will tell the kernel mode driver via I/O control to tell him that how you can interconnect with the how you can configure the hardware. Then the whole work will be done by user mode driver, kernel mode driver, and then the final hardware. But for the I think for the OpenCAPI's part, this is different, because for OpenCAPI we have virtual addressing, so this kernel mode driver is not needed anymore. So we can just remove this kernel mode driver, and then we just bridge this user mode driver directly talk with the hardware. And so this means that the software stack has been simplified, and the user, they don't need to maintain the kernel mode driver code, because this kind of driver is really complicated. They heavily rely on the GEM and DRM, which is generic, graphics engine management, whatever. It's a really complicated Linux modules that can manage the kernel mode memory map. So we can remove this part of kernel mode driver directly from the OpenCAPI software stack, so that we can bridge this user mode driver, and they can work well with the hardware. And for this different part of work, so for the training framework, it's already in the open source community, because you can use Caffe or TensorFlow or any other open source framework. And then for the compilers, NVIDIA just open sourced their compiler this September, last month. So we wait for 1 year. For last year, they open sourced their hardware from this side, and this year they open sourced their software compiler. So which means the final part of the whole ecosystem is finished. And then for all the other parts, it's already in the open source community. So this is the whole software stack for NVDLA, and there's also as I have said that this part is how OpenCAPI can help simplify the software stack. And then let's take a deeper look at what we have done for the software for simplifying the software stack. So for this whole picture, you can see that initially for NVIDIA software, they have the I/O control calls, and then they will call the kernel mode DRM driver, which has a very complicated memory management system. And then finally, this DRM driver will talk to the firmware, and finally, this firmware will talk with hardware via register read write. And for OpenCAPI, we just remove this, just change the user mode driver I/O control, just change it from I/O control call to direct function calls, because we don't need that I/O control to bridge from user space to kernel space. And then this whole DRM driver, which based on GEM, memory management, is removed in our software stack. And then we moved this whole firmware code from kernel mode to user mode. So you don't need to compile your code with a selling to Linux kernel. You don't need that anymore, because if you want to compile a driver, you need to download the Linux headers. So in our case, you don't need that anymore. So you just put this code into a regular makefile, and to feed it with correct dependencies and flags, then everything is okay. Just make, then you don't have extra dependencies for this whole software stack. Okay. And then this is the result. Right now we are running this the whole project with Emin Hawk in Austin Lab, and we are just, as I have said, we are running this with AD9H7 alpha data card. And then right now we are running with a large configuration of NVDLA, which has 2048 max, and the whole clock frequency is 200 megahertz on our FPGA. So and all the functional tests has been passed for our test, and we also try to run an AlexNet and on some pictures. So this all work is in progress. We are trying to tune the accuracy of the whole system, and the major work is on the software side, because we need to understand their compiler settings. We need to pick the correct models, and we need to compile this model to a really workable, loadable format binary. So this whole work is we also have a Snap 2 version last year. For this year, we have the OpenCAPI version. For the Snap 2 version, we're running it with Romulus power net system and another CAPI 2 version FPGA card, which is from vendors from China. And then okay. So this is the performance, and right now the performance is still under tuning. The projected performance for AlexNet and the ResNet 50 we have shown here for the NVDLA. But right now in the real system, we cannot run into this kind of performance, because we still have we are still working on the settings of the compiler, because the batch size of the model right now we are using is not optimized, and we expect to solve this problem by increasing the batch size. And this will be in our plan. Maybe within this year, we will tune the ResNet 50 to projected performance, and we are also working on bringing up the YOLO network for the NVDLA. And then this is FPGA implementation result on the AD9H7, and the whole I think this is the floor plan of the work, and the utilization is almost 50% for the LUT and 75% for the CLB, and we have 20% of the BRAM used for this NVDLA engine. And for the DSP, we only use less than 3% of the DSP. The reason is that right now our settings because I've mentioned that NVDLA they have 2048 max. We have two options, so we can construct those max with LUT, with LUT. We can also choose to implement them with the DSP in the FPGA. So we try to compare the different settings. If we choose to use the DSP, then the utilization of DSP will be 33% of the FPGA, and the LUT usage will decrease to 40%, from 47 to 40% of LUT utilization. But in this implementation, we don't feel it is necessary, because we still have a huge room for the LUT utilization, so we don't choose to use DSP. But in the future, maybe right now we are working on that. If we have multiple engines, if we put maybe two NVDLA large configuration into this FPGA, then we need to use the DSP, because the room for the LUT will be not sufficient, will be insufficient for two NVDLA. But this is our future work. Okay. And then here is the summary. So right now, I think NVDLA and OpenCAPI is a good example to show that how open hardware ecosystem, how open hardware community can work together to deliver a real business product. And then I think the next step of our work is to have larger configurations. Maybe we have two NVDLA, so that we can have 4097 max in total on the FPGA. And then the compilers and the parsers, we are still working on that to adapt more different models from ResNet to YOLO. And then the performance tuning and other real workload support is still in progress. And then every piece of this code are in GitHub, in the open hardware, in the open source community. And I have some pointers to different a piece of code in my slides. And then there's some reference for our work. And then I still have some more details in the following slides, but I will not go into details. So that's all from my side. So any questions?